Welcome back to The Explainer. Today we're going to do something fun. We are going to take one of the most famous rules in all of physics and crack it right open, because there's something absolutely incredible hiding inside.
Okay, so we've all heard it, right? Nothing can go faster than the speed of light. It's the universe's ultimate, unbreakable speed limit, period. But what if that's not really the whole story? What if there's a different kind of speedometer, one that we all have, that has no limit whatsoever?
So why the confusion? Well, the problem, and this is something physicist P. Frauendorf points out in the paper that inspired this explainer, is how we usually teach special relativity. It gets presented as this weird, abstract mathematical thing, It's always tacked on at the end of the textbook, totally disconnected from everything else we learn about motion. But we're going to fix that today.
All right, Section 1, a broken speed limit. First things first, we're going to need to upgrade our intuition about what speed even is.
And that brings us to Section 2, one map, two clocks. This is the key. It's a simple little metaphor, but believe me, it changes everything. So here's how this simple idea works. It's just two steps. Step 1, the map. Imagine a single giant map of the universe. Everyone, you, me, a spaceship captain, we all agree to use this one map to measure distance. Simple enough. But now, step 2, the clocks. This is the secret sauce. The trick is, we're going to use two different clocks to measure time. Okay, so what are these two different clocks? Well, first, you've got the map clock. This measures what we call coordinate time. We'll just call it T. Think of it as the clock for a stationary observer, someone just watching everything unfold on that big nap. But then you've got the traveler's clock. This is literally the watch on the traveler's own wrist. And it measures something different, something called proper time, which we label with the Greek letter tau, or T. And this brings us to Section 3, the traveler's speedometer. Okay, so now that we have our map and our two clocks, we can finally unveil a completely new way of thinking about speed.
First, let's talk about the speed you're already familiar with, coordinate velocity, or v. This is just the distance you travel on that big universal map divided by the time that goes by on the map's clock. This is the one we always talk about, the one that has that famous speed limit, c, the speed of light. No surprises here.
But here is the breakthrough. Proper velocity, which we'll call w, you calculate it using the same map distance, but you divide it by the traveler's time, the time on their own watch. This is the speed the traveler actually experiences. And because time literally slows down for that traveler as they get closer to light speed, their proper velocity, the distance they cover per second on their own clock, can just keep going up and up and up. It has no upper limit at all.
And you gotta love this. There's a fun little bit from the paper that inspired this. To make this idea stick, some students call one unit of proper velocity, that's one light year of travel in one traveler year of time, a Roddenberry. Named after the creator of Star Trek, a show that was pretty famous for not letting the speed of light get in the way of a good story. Which leads us to Section 4, relativity made simple. So you might be thinking, okay, that's a cool trick, but why does it matter? Well, because this one simple concept, proper velocity, takes some of the most confusing parts of physics and makes them, well, shockingly simple. I want you to think way back, maybe to your first high school physics class. Do you remember the first equation you ever learned from momentum? It was probably something really simple, right? Well, just look at this. In classical physics, the stuff Newton taught us, momentum p is just mass m times velocity v. Easy. Standard relativity makes this equation way more complicated. But when we use our new proper velocity w, the equation becomes beautiful again. Momentum is simply mass times proper velocity. P equals mw. It's just clean. It's elegant. And this one little change makes a huge difference. Momentum becomes simple again. We don't need confusing ideas like relativistic mass anymore. Suddenly, those really difficult high-speed problems become much more accessible. The physics of it all just starts to feel, well, intuitive. Okay, that's the theory. Now for Section 5, an Andromeda road trip. Let's really put this idea to the test with a mind-blowing thought experiment. And this comes straight from the research.
So imagine we're going to take a trip, a big one, to the Andromeda Galaxy. And to make it a smooth ride, will accelerate at a constant 1g. That's the same gravitational pull you're feeling right now, for the first half of the trip.
Now here's the question. According to the traveler's clock, the watch on their own wrist, how long does that first half of the journey take? The answer is just 14.2 years. Yeah, less time than it takes to grow up, basically.
But in those 14.2 traveler years, how much distance did our ship actually cover on that big universal map? Get this, over 1,100,000 light years.
Just let that sink in for a second. This isn't science fiction. This is what the established laws of relativity tell us. A journey across more than 1 million light years of empty space could feel, to the person on board, like it takes less than 15 years. That is the power of thinking in terms of proper velocity.
And this really gets to the heart of it all. The paper puts it beautifully, saying that the story of increasing proper velocity thus goes untold to a public whose imagination might be captured thereby. By only focusing on that external speed limit, we've been missing the real story, a story that could totally capture our imagination.
And this isn't just a thought experiment. Look at this. It's the real-world land speed record. You take an electron at CERN, right? Its coordinate velocity, v, is so close to the speed of light, but it can never quite get there. But its proper velocity, w, from its own point of view, that same electron is covering distance at a rate that's like 100,000 times the speed of light. That is 100,000 Roddenberries.
So here's the big takeaway. The real story of progress in space travel might not be about getting closer and closer to some external universal speed limit. Maybe the real story, the real measure of our ability to explore the cosmos, is about how much distance we can cover in our own very finite lifetimes. It turns out the only speedometer that really matters is the one on your own wrist.
And it just makes you wonder, doesn't it? If the universe's ultimate speed limit isn't the brick wall we always thought it was, what other so-called impenetrable limits are out there? Just waiting for a new clock, a new map, or maybe just a new way of looking at things to see right through them. Thanks for joining us on The Explainer.